previous lecture, near the end of the previous lecture, we had started with the solution of the particle in a one dimensional potential well. We will continue with that, and we hope that today we will be able to start this solution corresponding to a particle in a three dimensional box, which has many important applications. So, let us start with the one dimensional potential well problem, in which the potential is 0 between x less than a by 2 and lying between minus a by 2 and plus a by 2 and V 0 outside. So, the particle is confined in this well, and we had solved the Schrodinger equation. This is the origin. Since V of minus x is equal to V of x, the potential is symmetric. So, the wave functions are either symmetric or anti-symmetric. We first considered the symmetric wave functions, and we solved, and we found that the solution of the Schrodinger equation in region 1 was equal to a cos k x, and the solution in the second region, this is in the first region, and in the second region was equal to c into e to the power of minus kappa x. So, you have here an exponentially decaying solution in the second region. We then match the wave function at x is equal to a by 2 and its derivative. So, we got two equations, a cos k a by 2 is equal to c into e to the power of minus kappa a by 2. This is the continuity of the wave function at x is equal to a by 2, and the continuity of the derivative will be, if I take the differential, minus k a sin k a by 2 is equal to minus kappa c e to the power of minus kappa a by 2. And if I divide for non-trivial solutions, as we discussed last time, if I divide one with respect to the other, we will have k a by 2 tan k a by 2 is equal to kappa a by 2. We write this as xi, this quantity as xi. So, xi tan xi is equal to eta, where eta is equal to kappa a by 2. So, we know that xi square is equal to k square a square by 4, or this is equal to 2 mu e a square by 4 h cross square, and eta square is equal to kappa square a square by 4. So, kappa square is equal to 2 mu v 0 minus e a square by 4 h cross square, and xi square plus eta square. If I add these two equations as we had done last time, so the e will cancel out. So, we will get 2 mu v 0 a square by 4 h cross square, which is a constant. So, this I put as alpha square. So, then eta square is equal to alpha square minus xi square, and so therefore, eta will be equal to alpha square minus xi square. So, you see, for a given value of mu, for a given value of a, and of course, h cross is a constant, the only unknown parameter is xi e, and therefore, xi. For a given potential well, alpha is known, because mu is known, V0 is known, A is known, H cross is a constant. So, alpha is a number. We will discuss a very simple example little later. So, therefore, the transcendental equation is xi tan xi for symmetric states is equal to alpha square minus xi square. We set both of them equal to eta. So, what we do is that we plot the left hand side and the right hand side as a function of xi. Now, what is the right hand side? So, as we have seen that if I square this, so I get alpha square minus xi square is equal to eta square. So, xi square plus eta square is equal to alpha square. So, this is the equation of a circle in the xi eta plane. X square plus y square is equal to alpha square is the equation of a circle of radius alpha. Now, the left hand side, as you know that tan xi is equal to 0 for xi is equal to 0, pi, 2 pi and 3 pi, and tan xi is equal to infinity, actually plus or minus infinity at pi by 2, 3 pi by 2 and so on. So, let me plot this carefully. So, I have here the horizontal axis is xi. So, at xi is equal to 0, it is 0 and it will go to infinity at pi by 2. And then there is a discontinuity like this, and then it will become infinity like this, because tan xi has an infinite discontinuity at pi by 2, and it will become 0 at pi, then it will become infinite at 3 pi by 2 and so on. So, this is the plot of xi tan xi as a function of xi. It will have infinities at pi by 2, 3 pi by 2, 5 pi by 2 and so on, and it will have zeros at 0, pi, 2 pi and 3 pi. Now, this is the left hand side. Let me now plot the right hand side. Right hand side is this is the eta axis. So, eta square is equal to under root of alpha square minus xi square. So, this is the quadrant of a circle. So, I will ask you that tell me the value of alpha. If alpha is 2, then I will draw a circle, a quadrant of a circle. This is pi by 2, that is 1.5. So, 2 is somewhere here. So, if alpha is 2, I will have a circle of radius 2. Then at this point, the left hand side and right hand side are equal, and the value of xi is, let us suppose, something like say 1.4 or something like that, and that is a eigenstate of the problem. Let us suppose, what is alpha? Alpha, as I told you, is under root of 2 mu V0 a square by 4 h cross square. If it was 4, let us suppose alpha is 4, then I have to draw a circle of radius 4 units. So, pi is here, 3 pi by 2 is here. So, 4 will be somewhere here. So, I will draw a quadrant of a circle of radius 4, and then there will be 2 places where the left hand side will intersect the right hand side, and there will be then 2 states, 2 symmetric states. We have considered only till now the symmetric states. We will consider the anti-symmetric states in a moment. So, these are the discrete eigenvalues of the problem. And whenever you have an equation like this, we say it is a transcendental equation. It is satisfied only when the left hand side is equal to right hand side, and that will happen only for certain discrete values of xi. If xi was equal to say 8, then you will have to draw a circle of radius 8, say alpha is 8, then you will have 3 symmetric modes. I hope you understand what I am trying to say. So, let me skip here for a moment, we will come back to this figure a little later and consider the anti-symmetric states. So, we go back to the potential well that we had discussed earlier, that I have here this as the potential well. Till now we had considered symmetric states in which the solution that we had taken was cos k x in this region. Now, in this region 1, so region 1 is x less than a by 2, the Schrodinger equation is d2 psi by dx square plus k square psi of x is equal to 0. So, solution can be either cos k x or sin k x. So, we now consider the anti-symmetric solution. The anti-symmetric solution. In the anti-symmetric solution, we will have in the region x less than a by 2, you will have psi of x is equal to a sin k x, a sin k x. And for x greater than a by 2, we will have again the same solution. The Schrodinger equation will be d2 psi by dx square minus kappa square psi of x is equal to 0. So, the solutions will be psi of x will be an exponentially decaying solution minus kappa x. Once again, we match the we apply continuity conditions. The continuity of the wave function will be a sin k a by 2 will be equal to c e to the power of minus kappa a by 2. At x is equal to a by 2, psi of x should be continuous. And then I have the derivative continuous, that is k a cos k a by 2 is equal to, with a minus sign, kappa c e to the power of minus kappa a by 2. So, I again divide this equation by this equation, the a's cancel out. So, for non-trivial solution, you will have k, I multiply by a by 2, k a by 2 cot k a by 2 is now equal to minus kappa times a by 2. The value of kappa is still the same, which is equal to 2 mu by h cross square V 0 minus E. So, once again I will have the similar kind of a thing. So, I take the minus sign here. So, I get minus xi cot xi is equal to kappa a by 2, that is eta, and that we had shown to be equal to under root of alpha square minus xi square. So, the right hand side remains the same. So, we summarize the results. So, for the symmetric solutions, we had xi tan xi is equal to under root of alpha square minus xi square and minus xi cotangent of psi is equal to under root of alpha square minus xi square. So, this I put equal to eta, this I put equal to, this corresponds to symmetric states, and this corresponds to anti-symmetric states. Now, let me plot it again. So, we will have something like this, and let me do. So, let us suppose this is pi by 2, this is pi, this is 3 pi by 2 and so on. So, xi tan by is goes to infinity here, it goes like this, like this. So, this you have pi by 2, 3 pi by 2 and 5 pi by 2, and this will go to infinity. This is what I have plotted is xi tan xi as a function of xi. So, this is eta. Now, let me plot if I have a red pen, let me plot minus, oh I am sorry, this is not COST, this is COT, I am sorry. So, this is COT, cotangent. So, cotangent xi times cotangent xi tends to a finite number at xi equal to 0, because cot xi tends to infinity, xi tends to 0. So, the product is, so it is something like this at pi by 2 cot xi is 0. So, it is something like this. It will go to infinity at pi, and then it will go like this at pi 5 by 2 it will go to infinity. So, this is my, this quantity is which I have shown with red pen xi cot xi, and then there will be again at 5 pi by 2, then this will be at this point it will be infinity. So, something like this. The right hand side, let me, if I have another color, is a quadrant of a circle whose radius is alpha. So, let me first take alpha is equal to 2. So, if alpha is equal to 2, the quantity 2 is less than pi. So, the quadrant of the circle will be something like this. This is pi by 2. So, as you can see, there will be one symmetric and one anti-symmetric state. If alpha was equal to 1, this is alpha equal to 2. If alpha was equal to 1, then this will be only one symmetric state, only one discrete state. If alpha was 4, then this is the radius which is greater than pi, then there will be two symmetric states and one anti-symmetric state. And let us suppose alpha is 6, then you will have to draw a radius of 6, then it will be two symmetric states and two anti-symmetric states. As the value of alpha becomes larger and larger, that is, as the value of V0 becomes larger and larger, we will have larger and larger number of states, discrete states that are possible. In general, a potential well has a finite number of states. It has a finite number of discrete states. And how to determine the number? I will tell you that give me the value of mu, give me the value of V0, give me the value of A, and I know H cross. I will first calculate the value of alpha. If the value of alpha is less than pi by 2, I know that there is only one symmetric state. If alpha lies between pi by 2 and pi, there will be one symmetric and one anti-symmetric. If alpha lies between pi and 3 pi to pi by 2, then two symmetric and one anti-symmetric, and so on. So, let me consider a simple case, a proton in a potential. So, I assume that the mass of the particle is the proton mass, and the proton mass is about 1.67 into 10 to the power of minus 27 kg. Let us suppose this approximately represents the deuteron problem 25 MeV. This is the, so this is about 4 into 10 to the power of minus 12 joules, 25 MeV, and A, the range of the potential, we let us suppose this is equal to 3.65 into 10 to the power of minus 15 meters. 10 to the power of minus 15 meter is known as a Fermi, in honor of the famous nuclear physicist Enrico Fermi. 3.65 Fermi. 1 Fermi is 10 to the power of minus 15 meters. And you know the value of H cross, which is about 10 to the power of H cross is about 10 to the power of minus 34 joules second. It is always better to use consistently the MK system of units, then there is no chance of an error. If you substitute the values of this, so you substitute this is equal to 2 mu V 0 A square by 4 H cross square. You substitute for mu so much 1.67, V 0 is 4 into 10 to the power minus 12 joules, A is 3.65 into 10 to the minus 15, H cross is 10 to the power minus 34. If you substitute that and take the under root, you will get alpha is equal to 2.0. So, if alpha is 2.0, so then alpha lies between pi by 2 and pi, and therefore, there will be 2 symmetric states. So, there will be 2 states, one symmetric and one anti-symmetric. The corresponding values of eta, for which the left hand side is equal to the right hand side, this is equal to 1.02987. It can be obtained very easily, and the corresponding value of E comes out to be I am sorry, this is the value of xi. This comes out to be 6.63 MeV, and the other value is 1.89549. The corresponding value of E is 22.45 MeV. So, you see what the value of xi is. For example, here let us suppose this is the alpha is equal to 2. So, this is the value, the first value of xi, and this is the second value of xi. These are the discrete energy eigenvalues of the problem. So, therefore, we obtain 2 states, and so for this particular problem we have obtained that you have this potential well, and the first, the ground state has this, the depth is about 25 MeV, this is 25 MeV, this is 25 MeV, and here is the first state which has 6.63 about, this is the first state, and the wave function will be a symmetric wave function like this. It will be cosine solution here and exponentially decaying solution here. And the second one, which is right at the top, is it has a value of about 22.45 MeV, and it will be an anti-symmetric solution. So, it will be 0 here and something like this. I hope you, this is a symmetric solution, cosine inside and outside it is exponential, and this is an anti-symmetric solution. You remember, if you recall, we showed that in the harmonic oscillator problem, they were alternately symmetric and anti-symmetric. First the ground state is symmetric, then anti-symmetric, then symmetric, then anti-symmetric, and so on. The same is true in all cases, that you will have first the symmetric state, then anti-symmetric, and in this particular case there are only two discrete states. There are only finite number of discrete states. If it were instead of 25 MeV, if it were 250 MeV, then there would have been a much larger number of states. So, a finite number of discrete states. I would like to conclude this discussion by mentioning that we have considered only 0 less than E less than V 0, and we have obtained, we have shown that we will have a finite number of discrete states. E can never be less than 0, because no condition can be satisfied. E can never be less than 0, then the minimum value of the potential energy. E can of course be greater than 0. E can be of course greater than 0. Then once again you will have a particle which comes in from the left and will get reflected and will get transmitted. So, therefore, in this particular case, what I told you at the end is important, that you have two states, two types of solutions. One, discrete bound states in which the wave function is exponentially decaying at large distances, and then you have incident wave and the reflected wave, and so you have a finite number of discrete states for E lying between 0 and V 0, and a continuum of states that is all possible values of energy for E greater than V 0. These are also known as scattering states. Now, in all problems of quantum mechanics, for a given potential energy distribution, you have two types of solutions. One is the discrete bound state solution, and the other is the continuum of scattering state solution. And the simplest example that I could think of is this simplest atom, hydrogen atom. We will discuss that in greater detail later. But the hydrogen atom, you know, it consists of a proton and an electron, and there are two types of solution. One in which the electron and the proton are together to form a bound state, and you have discrete energy levels of the atom. These are the discrete bound states of the Schrodinger equation. And the second is, let us suppose proton is here and the electron is coming from a large distance. Proton is coming here and the electron is coming and getting scattered. Here it is a continuum of energy values, all possible values of energy are allowed, and these are the scattering states. So, in the hydrogen atom problem, you will have the potential energy function is given by minus ZE square by R, and if you plot this ZE square by R minus ZE square by R, then you will have a set of discrete state, in fact infinite number of discrete states. These lead to the hydrogen atom spectrum, and for E greater than 0 you will have a continuum of states in which a particle will come from large distance, interact with the proton and get scattered. That is the famous Rutherford scattering that hopefully we will discuss at a later time. So, till now we have considered 4 or 5 problems. First, we considered the free particle problem, in which the potential energy is 0 everywhere, and we found only plane wave solutions, continuum of wave functions, and we found that this was I p x by h cross. These are the wave functions, the psi p of x, all values of energy are allowed. You normalize this by putting 1 over root 2 pi h cross. Then you consider a particle in an infinitely deep potential box, where this is infinite. Then you have only discrete states, no continuum states, only discrete states, and we had psi n of x is equal to a, the normalization constant, sin n pi x by L, and you have a from 0 less than x less than L. Then we consider the harmonic oscillator problem, in which there is V of x is equal to half mu. This also has an infinite number of discrete states, and the wave functions are, as I have told you many times, these are the Hermite Gauss functions. Then finally, we considered a potential well problem, and in which there are two classes of solutions. One, discrete bound states, finite number of discrete bound states, and for E greater than 0, you have a continuum of states. These are the scattering states. And then we considered this problem of this barrier problem. If I consider this problem, then there are no bound states, only all values of E greater than 0 are allowed. These are a continuum of scattering states. So, if you solve the Schrodinger equation for a given potential distribution, we have considered consistently only one dimensional potential problems, then you will get two types of solutions. One in which the particle is confined near the origin, those are the discrete bound states of the problem, and the energy levels are discrete, and then you have in addition a continuum of scattering states, which may or may not exist. For example, in the case of the harmonic oscillator problem, or in the case of a particle in an infinitely deep potential well problem, there are no scattering states. There are no scattering states. So, this almost completes the analysis of one dimensional problems. Today, I want to continue the discussion and consider a very simple and very important problem of particle in a box, and it very accurately represents the free electrons in a metal. So, we start with the, so we do the particle in a 3-dimensional box, and of course, we have to solve the 3-dimensional Schrodinger equation. This is probably the simplest and a very important solution of the Schrodinger equation. So, the 3-dimensional Schrodinger equation is given by del square of psi plus 2 mu by h cross square E minus V psi of x y z is equal to 0. Now, I consider an electron or a proton which is confined inside a box, whose side is L. That is what I mean by confined. It is an infinitely deep potential well, but it is a 3-dimensional box. The particle cannot go out of the box, and therefore, the wave function has to vanish at all points on the surface of the box. So, for example, if I take this as my x axis, so this plane is x is equal to 0, and this plane, this side is x is equal to L. And similarly, if the vertical axis is the z axis, then the base is z is equal to 0, and the top one, the top roof is z is equal to L. And of course, for a problem like this, one has to use Cartesian system of coordinates, and therefore, the del square psi operator becomes delta 2 psi by delta x square plus delta 2 psi by delta y square plus delta 2 psi by delta z square, and inside the box the potential is 0, and so therefore, V is 0. So, you get 2 mu E by h cross square psi. So, that I represent by k square psi is equal to 0, where k square, let me write it down by red, that k square is defined to be equal to once again 2 mu E by h cross square. Now, I want to solve this problem. So, once again I have a box of length, or I have a metal, for example, I have a metal cube, each side is of length L. There is an electron free inside the metal, but the potential is so deep that it cannot escape from the metal. So, the wave function associated with the electron must vanish on the surface of the metal. So, let me solve this equation then and apply the boundary condition that on all 6 faces the wave function is 0. So, we use the method of separation of variables. So, this is the method of separation of variables, and we write this as psi of x, y, z as equal to x of x, y of y and z of z. Let me try this out. This is a method which sometimes works, sometimes it does not work, but in this case we know that it will work, therefore, we are using that. So, what is delta 2 psi by delta x square? So, this will be delta 2 psi by delta x square will be equal to this, and this will be constant. So, y and z can be, and this then becomes a differential d 2 x by dx square, and similarly delta 2 psi by delta y square and delta 2 psi by delta z square. So, if I substitute this solution in this equation, then what I will get is the following: y times z into d 2 x by dx square. Remember that we have assumed that, let me do this again. So, we have assumed that psi of x is equal to x, y and z. So, we substitute it in this equation. So, we will get y z d 2 x by dx square, then x y d 2 x z d 2 y by dy square plus x, the third term will be x y d 2 z by dz square plus k square into psi. Psi is x y z, x as a function of x, y as a function of y and z as a function of z. So, I substituted this solution in this equation and I obtained this, and the next is very simple, that I divide the whole equation by psi, that is I divide by x y z. So, I get 1 over capital X d 2 x, this is very straightforward, d 2 x by dx square plus 1 over y d 2 y by dy square plus 1 over z d 2 z by dz square plus k square, k square, and this will cancel out. So, this I write as minus k square. Now, this is a function of x, this term is a function of y and this term is a function of z. How can a function of x plus a function of y and plus a function of z be equal to a constant? because x, y, z are independent variables. It could only happen if each term is a constant. So, I write this must be equal to, let us suppose, minus k x square. You cannot set it equal to a positive constant, because then, as we will show later, it will not be able to satisfy the boundary conditions. This will be equal to minus k y square, and this will be, I set that equal to minus k z square. Then you will have k square is equal to k x square plus k y square plus k z square. K x, k y, k z are just, these are numbers, these are just symbols. So, let me write down this equation. So, 1 over x d2 x by dx square, I have set this equal to a minus of a constant, I have set this equal to k x square. So, therefore, if I multiply this out, this will become d2 x by dx square plus k x square multiplied by x of x is equal to 0. Now, of this equation, this is a simple second order equation, and I know the solution, and the solutions are x of x is equal to a sin k x x plus b cos k x x. Now, if this is the x axis, then the wave function has to vanish on all points on the plane x is equal to 0 and on all points on the plane x is equal to L. So, the wave function has to vanish. So, if I put x is equal to 0, the wave function has to be 0. So, 0 must be equal to, this is 0 plus b at x is equal to 0. So, therefore, this will give me b equal to 0. So, this term goes out, b is equal to 0. Then we have at x is equal to L, the wave function must be 0. So, 0 is equal to a sin k x L. As we had done quite some time earlier, there are now two possibilities. One is that either a is 0 or sin k x L is 0. If a is 0, then the wave function is 0 at all places. So, psi is equal to 0 everywhere. That is known as the trivial solution. So, a cannot be 0. So, we can have only sin k x L must be 0, and so therefore, which will imply k x L is equal to n x pi, where n x will be not 0, because again if it is 0, then k x is 0. If k x is 0, then the wave function is 0 everywhere. So, that is again a trivial solution. That is again a trivial solution. So, you will have the allowed values of k x are n x pi by L, where n x is equal to 1, 2, 3, 4, 1. Similarly, we have solved this equation. Similarly, I can solve this equation. Similarly, I can solve this equation, because the y equation is 1 over y d2 y by dy square is equal to minus k y square So, that will lead to this will lead to the equation d 2 y by dy square plus k y square y of y is equal to 0. Once again we will have sine and cosine and exactly the same way. So, we will find that the allowed values of k y will be n y pi by L, where n y also takes the same set of values 1, 2, 3 etc. And finally, the z component, the z k z will be n z pi by L, and n z takes also this thing. So, you will have, if you recollect, that therefore, we had k x square plus k y square plus k z square was equal to k square. This is equal to 2 mu e by h cross square. Now, we find that k x takes discrete values. So, you have n x pi by L whole square plus n y pi by L whole square plus n z pi by L whole square. This is equal to 2 mu e by h cross square. So, I bring it to the left hand side. So, we have 2 mu e by h cross square is equal to n x square plus n y square plus n z square times pi square by L square, and we get the remarkable result that the energy levels are discrete, and you will have pi square h cross square by 2 mu L square n x square plus n y square plus n z square, where n x, n y and n z, they can each take the values 1, 2, 3, this. So, these are the discrete values of the energy, and corresponding to each set of n x, n y, n z, we have a wave function, and that is k x was equal to, if you remember, k x is n x pi by L. So, the wave function will be some normalization constant, which I can show to be equal to under root of 2 by L whole cubed sine of n x pi by L into x sine of n y pi by L into y sine of n z pi by L into z. This is 0 less than x y z less than L inside the box. So, these are the normalized wave functions, and these are the discrete states. So, what is the ground state value? The ground state value is n x is equal to 1, n y is equal to 1, n z is equal to 1. So, 3 pi square h cross square by 2 mu L square. So, you have here, if you plot this E, then the ground state is something like, say, 3 E 0, where you see the allowed values of E is, say, E 0 n x square plus n y square plus n z square. E 0 is equal to pi square h cross square by 2 mu L square. So, if n x is 1, n x y is 1, n z, that is the ground state. So, this is 1 plus 1 plus 1, that is 3. Then you will have 2 1 1 1 2 1 1 1 2. That state will be threefold degenerate state, and this will be 4 plus 1 plus 1, that is 6 E 0. So, this will be 2 1 1 1 2 1 and 1 1 2, and then you can have 3 1 1, that is 7 E 0, 3 1 1 1 3 1 and 1 1 3. So, that is 7 E 0, and so on. You can write down the various states very quickly. There will be, for a given set of for a given value of E, there will be many sets of integers whose sum of squares is a given number. So, I have been able to obtain the exact solution for a particle in a 3-dimensional box, for an electron confined in a cube of volume L cubed, and have been able to obtain the exact wave functions and the exact energy levels, and there are an infinite number of states. What I would like to calculate, and what is of extreme importance in solid state physics and in astrophysics and in many areas, is to calculate the density of states. That is, density of states meaning that when the energy levels become very large, the states are very closely spaced and there are very large number of states, and G of E d E represents the number of states whose energy lies between E and E plus d E. Once again, G of E d E represents the number of states whose energy lies between E and E plus d E. So, say let us suppose I want to find out the total number of states which have energy less than E, then n of E will be equal to 0 to E G of E d E. This is the density of states and this is the total number of states whose energy is less than E. There is a difference in dimension between n of E and G of E. One has to be a little careful. G of E represents the density of states, so that G of E d E represents the number of states whose energy lies between E and E plus d E, and n of E will represent the total number of states whose energy is less than E. Now, that the quantity, and if I am able to find out n of E, then of course, I can differentiate n of E to obtain G of E, because n of E is given by this n of E plus d E. I can write this down as 0 to E plus d E, and if I subtract one from the other, so n of E plus d E minus n of E is then equal to from E to E plus d E, G of E d E. So, in this small interval, this becomes equal to G of E d E, and so therefore, G of E is equal to n of E plus d E. So, G of E will become n of E plus d E minus n of E divided by d E. If d E is extremely small, then d n by d E. So, if I am able to find out n of E, then a simple differential will give me G of E. So, in my next class, in my next lecture, what I will do is that I will obtain an expression for n of E and obtain the density of states. and thereby we will be able to obtain the property of the electron inside a metal. A similar kind of analysis can be applied even for the electrons inside a white dwarf star. So, we will probably discuss that very briefly. Thank you.